Today's lecture concerns continuous random variables. After the last lecture, we're all now familiar with the discrete random variables. Today we're going to focus on initially the continuous uniform random variable. It's an easy generalization from the random variable we use to model the single six-sided die. Then we're going to talk about and refresh what convolutions are, what standardization is, and we're going to talk about limit theorems and hopefully get a rudimentary proof for the central limit theorem. To begin with, let's recall the discrete uniform random variable. And of course, we use this to model the six-sided die. If you recall, we've previously shown that the expectation of the random variable is just the middle point in this case. So for a six-sided die, it's 3.5. We talked about how we calculate the variance and how we calculate the moment generating function. But what we want to do is keep this random variable in mind, and we're going to use it to generalize to a new idea. The continuous uniform random variable, we think of this as modeling a spherical die, right? So this spherical die, instead of having six sides, has an infinite amount of sides, right? Because there's an infinite amount of points on the sphere that could be on the bottom or the top. So now say the sample space is any value from 0 to 6. So that could be 1, 2, 3, 4, 5. It could also be 1.5. It could be 3/4. It could be pi. It could be e. It could be irrational. It could be irrational. It just has to be a value between 0 and 6. What's the relationship between the discrete uniform random variable and the continuous uniform random variable? And what we can see here is that if we say, look at our continuous uniform random variable, and we collapse we collapse the probability on 6 intervals, meaning we collapse the probability between 0 and 1, and we assign it the event 1. We collapse the probability between 1 and 2, and assign it to 2. We collapse the probability between 2 and 3, and assign it to 3, and so forth. If we do that, we just get the discrete uniform random variable. So the continuous random variable just has an infinite set of outcomes, and the discrete uniform random variable can be looked at as the same thing, but partitioned into 6 sections. One thing that's important to understand is the PDF for the discrete uniform gives you the probability of that observation occurring. Whereas for the continuous random variable, it gives you the height at that point. So what we call that is the density. But of course, the probability at any point with a continuous random variable is 0, because there's an infinite amount of possibilities. So the probability of 1 out of an infinite set of events is of course 0. And of course, finally, we don't want to forget that we need to mention that the cumulative distribution function on a continuous random variable is, instead of being a sum over a series of events, is an integral, which of course we can think of as an infinite sum over some range. And so at the bottom of the screen, we see how we actually can move between the discrete and the continuous versions of the random variable. So we can say that if we want to know the probability of KD, where K is some discrete value or some range, so for example, let's say that K is 3, is equal to the distribution function at 3 minus the distribution function at 2, which is just the integral of the density function from 2 to 3. So that's actually easier, because integrals are easier to take than sums. The formal statement for the convolution in the discrete space, right, is the probability that some random variable z equals some value lowercase z is just the sum over all values where x equals k and y equals z minus k. Because of course, only when y equals z minus k and x equals k does z equal z. So of course, we can just sum over all the values for x and just calculate the probability of x equaling that value and y equaling z minus that value. And this, of course, is assuming that the two random variables, x and y, are independent. And so this is our formal definition for the convolution. And of course, this will generalize very, very nicely to the continuous space, where instead of being a sum over the values for x and y, it'll be an integral. Let's refresh something that we talked about back in the beginning of the class. We talked about how do you model the probability distribution of 2 dice, right? So you're taking 2 dice and you're throwing them and you're going to calculate the sum. And so you want to talk about that probability. And of course, that probability is not a uniform probability distribution, because we know that the most common value to see when you throw 2 dice is actually a 7. And here you can see why. So you can see that the convolution for 7 has sort of the most possibilities because it's a discrete uniform random variable. They all have the same probability, right? So the probability of any occurrence of the 2 faces of your die is 1 over 36, because they're both independent and all probabilities are 1 over 6. Of course, we'd rather have a closed form solution. So to do that, we notice a few things. What we notice is that, of course, the probability is minimized at the extremes, because there's only one way to see 2 copies of the minimum value of the die or 2 copies of the maximum value. So obviously 2 and 12. We also notice that the probability is maximized at the middle value of the die. We also notice, of course, that for any single combination, the probability of that observation is 1 over 36. So we can think of our probability distribution function as some function that's going to give us some number over 36, where the numerator is going to be the number of ways of observing your value, right? What does that look like? We notice that that looks sort of bell-shaped. Obviously, it's highest at 7, and it drops down linearly until you get to the 2 extremes. As the convolution is easy to write, but hard to express in a closed form, we had to do a little bit of logic to figure out what the closed form solution is. Luckily, in the continuous world, it's actually easier. Same idea. And we say, okay, well, what is that? Well, of course, we know what P of x is. P of x for all x is just 1 over 6, because that's the height that will make the probability distribution function equal to 1. Pull that out of the integral, and then we can say, okay, well, in the case that z is less than 6, you're going to be going from 0 to z. Of course, it's just going to be z over 1 over 6 times 1 over 6, which is going to be z over 36. And then if z is greater than 6, that's the same integral, but now you're going to be going from z to 12. So it's going to be 12 minus z over 36. So of course we can see that by evaluating the integral at the 2 pieces, we get a triangle. So we just added 2 discrete uniform random variables to represent the summing of 2 dice. And we also showed how we can just calculate the convolution to get the probability distribution function for 2 continuous dice, or 2 continuous uniform random variables. And now we're going to just say, okay, let's just look empirically at what happens when we add more dice. And so the code's all online, and what this code does is it just tries exactly that, right? It looks at the distribution function as you add more dice. And what you're seeing here, hopefully, is that the continuous uniform random variable and the discrete uniform random variable, when you add them up and you take the random variable to equal the sum of those values, those look like the same distribution as you add more dice. The distributions obviously are changing, because as we add more and more dice, the expectation goes up. What we're going to do is, instead of calculating the limit distribution for the sum of n die, we're just going to take the sum of n die, and then we're just going to divide by n, right? So here you can see, of course, the expectation of the sum over n is always 3.5. And you can also see, for example, that the variance, of course, grows as you add more and more dice. But again, here we're just going to take that, we're going to take the variance of the sum of the dice divided by n. So our new random variable, instead of just being the sum, is going to be the sum divided by the number of dice. And now you can see that the variance is shrinking, actually, as you add more dice. So the expectation stays the same and the variance is shrinking. And hopefully we recall why that is. Variance of ax is going to be a squared variance of x. So that's going to be important for us to recall that that value gets squared, and that's why the variance of the total divided by n is shrinking. Well, what's the expectation of this random variable x bar? It's just going to be n times expectation of x divided by n, which is just going to be expectation of x, or mu. So we can say that's good. We realize that the expected value for the sample mean is mu. However, what's the variance of the sample mean? The variance of x1 plus x2 plus x3 divided by n, and of course we know because variance is non-linear, we have to factor out not an n, but an n squared. We're going to be left with a variance of x over n, or we can represent that as sigma squared over n, which means that the variance gets smaller. It implies the law of large numbers. So what that means is, as you add more and more copies of x, you calculate its sample mean. As you add more and more random variables, the variance will start to vanish. So basically you will, as you get closer and closer to infinity, you will approach the value of mu with no variance for your sample mean. This is what casinos rely on when they say that given enough trials they will win. Of course, the expectation of x bar is mu, and the variance of x bar is sigma squared over n. So of course the variance of x bar times root n over sigma is 1, which is important because this tells us how we can do something called standardize a random variable. We're now going to write that as a new random variable called z sub n, and z sub n is just going to be represented as x bar minus mu over sigma divided by root n. Of course, we should notice here that these are real parameters because here the values for sigma, the values for mu are the actual values for the random variable. So now we've turned our random variable for the sample mean into a random variable that has mean 0 and variance 1. But let's also pause and say that while we've been talking about this in terms of summing of die, nothing we've done in the last couple slides has been specific to dice. And what we're actually investigating is x bar, which is just the sample mean of any random variable. And the only assumptions that we've made about the distribution, of course, are that x bar, are that mu exists, and we know it, and that sigma exists, and we can calculate it, right? We have used what we know about sigma and mu, but besides that, what we've done so far is agnostic to the underlying random variable, but what we have now is some z sub n, whose mean is 0, whose variance is 1, and represents the standardized sample mean for any collection of sums of independent identical random variables. The way we're going to investigate z sub n is, of course, our favorite way, right? The moment generating function, but that can be confusing. So let's just do a quick recap. What is the moment generating function? Just real quick. Well, it's just someone figured out that if you, instead of calculating the expectation of x, if you calculate the expectation of e to the tx, then you get a function back where if you take its derivatives with respect to t, set them to 0, the order of the derivative that you take gives you the raw moment. So if you take the second derivative and set t to 0, you get the second raw moment, or e of x squared. And of course, why is this? It's because, of course, e to the x has a Taylor series notation. And we can see that when we're taking the derivative, we are getting rid of all the lower terms. So if we're taking, say, the second derivative, we're going to get rid of the zeros in the first moment, and we have a term for the second, third, fourth, and fifth moment. But then, of course, when we set t to 0, we lose all the higher moments, right? So taking the derivative gets rid of all the lower moments, setting t to 0 gets rid of all the higher moments, and we're left with only the moment that we care about, and this can be a lot easier to calculate. What's most important is that we also mentioned before that any distribution that has identical moments is identical. So the moments are deterministic of the random variable itself. So given that, we're going to analyze this z sub n in terms of its moments, or at least in terms of its moment generating function. The moment generating function is just the expectation of e to the t times z sub n. And when we write that out, we can of course factor that because we have a set of sums, right? And so we can say, okay, well, that's just going to be the expectation of e to the t y1 over root n times e to the t y2 over root n, and so forth. And we can say, okay, well, we know what that is, right? That is just going to be the moment generating function. So of course, we know that those are all identical. So it's going to be we're going to have to raise those to the nth power, right? So it's a product of n terms, and each term is the moment generating function, but instead of using the helper variable t, we now have to use a t over root n. Of course, to solve this, we can go to the whiteboard and we can write out what the moment generating function looks like.
Okay, so for the first step, we're going to exponentiate the entire limit to bring down the n and concentrate on what's in the box. For the second step, we're going to rewrite the fraction and make a substitution where g equals 1 over root n. Okay, next we will rewrite the function in terms of g and then invoke L'Hopital's rule for limits of indeterminate forms, differentiating the function twice until it's no longer in indeterminate form. Here we notice that we're taking the second derivative of a moment generating function as g goes to 0, which is of course just the second raw moment, or e of x squared. Because the underlying random variable z sub n is standardized, the second raw moment is just 1, and we just have to return t squared over 2 to the exponent, and we are finished. And so now we know that the moment generating function of the random variable z sub n is e to the t squared over 2. To figure out what the underlying distribution that creates that moment generating function is, we will work backwards. Because the integral is not dependent on e to the t squared over 2, we can just pull this term out and divide accordingly, and then rearrange terms, and we get a quantity whose value should be equal to 1 to provide us with the proper moment generating function. We can then rely on the fact that this quantity should be equal to 1 to provide us with the proper moment generating function, as well as the fact that the integral of p of z should be equal to 1 based on the definition of the random variable. And finally, we're going to rely on some algebra as well as the Gaussian integral to show that the substitution of e to the z squared over 2 causes both the moment generating function and the probability distribution function to converge to 1 over root 2 pi, which we then can use as a normalizing constant, giving us the random variable 1 over root 2 pi e to the negative z squared over 2. And finally, we can unstandardize our random variable by subtracting mu from z and dividing both the exponentiated term and the normalizing constant by sigma. This gives us a random variable that represents the additive sum taken from all distributions.
So that is the Gaussian random variable. And so what we've just proven, almost surely, which is a convergence joke, is that the sum divided by n for any IID random variable will converge to either the standardized normal, if we standardize x bar, or the Gaussian random variable. And we've done that how? But by using moment generating functions to both derive and prove the central limit theorem. So that's obviously amazing because it tells us it doesn't matter, if you have a Poisson or a beta binomial, or a exponential or a gamma or a beta distribution, right, or anything. If you add them up and divide by the total, you keep sampling, what do you get? You get a Gaussian random variable. So that's really important. However, you could think about that with a few more complex ideas, right? You can extend this, and we're not going to extend it because we're pretty satisfied with ourselves, right? We proved something pretty difficult. However, people who've come before us have already extended it for us, so we're going to learn a little bit about what they did. So the first guy we're going to learn about, full name is Alexander Mikhailovich Lutvanov, and he's a Russian guy. He looks very serious, as you can see, and what he did was show that the central limit theorem will also work even if you don't have the same random variables. So they don't have to be IID, as long as all the moments exist and the variances can't be too big. And what that really means is as n goes to infinity, the variance of each one has to vanish, which isn't actually much of a constraint, but this is what he showed. And he did this using the characteristic functions, which are like the moment generating functions, but they have an imaginary part. So they're a little bit harder, but same kind of idea. This is obviously really important because it says now what it's saying is you don't need to have a bunch of Poissons or a bunch of beta binomials or a bunch of exponentials. You can have any combination of them. Any combination of random variables, you add them up, you divide by the total, and that limit distribution is going to be Gaussian or normal. That's important. What's also important to know is that this guy, like many people who try to teach statistics, cut his work short. So he had trouble put out work because it was necessary for him to work out courses and put together notes and slides and videos. Well, he didn't make videos, but he would have, and it would have taken him even longer because editing videos is even harder. So appreciate this guy. He came up with this while also having to teach, which is a lot of work. I mean, and that probably made his life a little shorter, but he's definitely a math hero for us. But the second guy might be even more impressive. He showed that weighted sums of independent random variables will satisfy the central limit theorem as long as moments exist and are finite. He even showed that you don't have to make a caveat about the variance as long as the moments exist. So of course the variance can't be infinite, but even if it is very big, it still doesn't matter. You don't even need that. And what's cool about this guy is he didn't even use characteristic functions. He actually did it all using convolutions. So if you're interested and you want to know more about this, you can look up his proof. It's actually might be more elegant than Lyapunov's, although that one's probably a little bit easier to understand. This guy's also pretty cool because he's also a farmer. And in fact, when he wasn't doing good in math, instead of using teaching as his excuse, he used farming. And when he wasn't doing good in farming, he used math as an excuse, which is definitely a smart out. So you couldn't really say anything bad about the guy. So obviously he's really smart because he helped us learn more about the central limit theorem. Also really smart because he knew how to get out of trouble for his two jobs. Since then, people have kept working on this central limit theorem, and it's got extended even farther. So where has it been extended? Well, it's been extended into the multidimensional realm. So you have a multidimensional central limit theorem, still holds. You even have a version of the central limit theorem that works when you don't have independent random variables. We're going to close today's lecture by adding 4 more random variables to our probability distribution chart. So we, of course, are going to add the normal random variable, the standard normal, the continuous uniform, which was our first continuous distribution, and which we briefly mentioned, the log normal random variable. And so we're almost there. By the next lecture, we will have our chart actually completely filled out, and we will be able to concentrate on sampling. So I hope you guys were as excited as I was to learn about the central limit theorem and understand that that we today have talked about one of the most important things in the history of probably humanity, and I hope we're going to be able to use that for good. So I'll see you guys next time.